There are many applications of nuclear physics in our world. However, maybe the most tangible of those are in nuclear medicine, in diagnosis and in therapy. An important example of a therapeutical application of nuclear physics is the administration of the radioactive nuclide Iodine-131 at rather high doses to patients who suffer from thyroid cancer. The photo illustrates this therapy. The tag on the patient's wrist indicates that this patient, Claire, has received an iodine-131 activity of 2,960 megabecquerel, so almost 3 gigabecquerel, to treat a thyroid cancer. As all other iodine isotopes, the radioactive isotope 131 accumulates in the thyroid. There, it decays via beta decay to xenon-131, which has an atomic number of 54, one more than iodine, which has the atomic number 53. In this beta decay, a neutron has therefore been converted into a proton. After surgical removal of the thyroid cancer, it is common to treat remnants with radioiodine. Furthermore, the therapy is quite successful in the treatment of metastases in the thyroid. It is instructive to explore the nuclear physics concepts that underpin this successful medical treatment. Over a few days during this therapy, the patient is so radioactive that contact to other humans has to be restricted. The thyroid gland is an important part of our endocrine hormone-producing system. Other parts, such as the hypothalamus or the adrenal gland, are illustrated here as well. The illustration on the right shows that the thyroid gland sits right next to the trachea and the vocal cords. This is the reason why surgical operations on the thyroid are challenging. Often cancerous tissue cannot be completely removed. This is where the radioiodine therapy assists. Thyroid cancer is a relatively rare disease, accounting for approximately 1% of all new cases of cancer each year. Nevertheless, it represents the most common endocrine malignancy, and its incidence has been increasing over the last few decades. The reasons for this increase are unclear, but they are in part related to the improvement of diagnostic tools that allow early diagnosis. In therapy, the thyroid is typically removed by surgery. However, it is impossible to remove the organ completely, owing to the proximity of the vocal cords, important arteries and also nerves. Hence, in clinical normal practice, these remnants, along with any metastases, which in common with the thyroid itself are also iodine accumulating, are treated and then destroyed by radioiodine therapy. These diagrams show the incidence of thyroid cancer in Australia with time and with age group. Thyroid cancer is more common with females, about twice as common, than with males. At a rate of about 10 per 100,000, it is a very rare malignancy. The increase since the 1990s is explained with better diagnostics. As with other cancers, thyroid cancer is more common with older people. The cartoon illustrates how iodine-131 is administered to treat some cases of hyperthyroidism. It is a relatively straightforward procedure. The activity is administered orally either as capsule or in liquid form. The thyroid is the only tissue in the body that intakes and holds onto iodine. In fact, iodine is essential for the thyroid gland to properly function. Once swallowed, the nuclide is absorbed into the bloodstream and then concentrates in the thyroid gland, where it begins to target and destroy the gland cell due to its radioactive decays. The fast beta electrons that are emitted in the beta decays are accompanied by gamma rays. It is, however, dominantly the localized energy deposition associated with the beta electrons that destroys the tissue. Apart from the fact that iodine accumulates in the thyroid gland, Iodine-131 is also very useful for this treatment because of its short half-life of 8 days. That means the activity, the number of decays per time, is relatively large. The application of a radioisotope that is only available for a few days for treatment is only possible because it can be readily produced in a reactor. In addition to the nuclear physics associated with its use in nuclear medicine, the production of iodine-131 also involves a number of nuclear physics concepts and technologies. To ensure an effective use in medicine, the isotope needs to be produced regularly, and this can be achieved with two techniques. In the first technique, the iodine-131 is extracted from neutron-irradiated uranium, and in the second technique, it's produced via N-gamma reactions from tellurium. Irradiated uranium is first stored for 24 hours in order to allow the decay of short-lived products and treated with sodium hydroxide. After filtration, where uranium and certain fission products are removed, the filtrate is then acidified with nitric acid. On heating, radioiodine is then distilled over and collected in a trap, while the rest of the reaction mixture is treated further for separation of molybdenum-99 and other relevant fission products. In the second technique, in the N-gamma reaction on tellurium-130, tellurium-131 is produced because the neutron is absorbed. The target material for the irradiation is typically tellurium oxide or sometimes tellurium metal, depending on whether a wet chemical separation or a dry distillation method is used. Iodine-131 produced in one of those ways is commercially available in dilute sodium hydroxide solution and with high radiochemical purity. The diagram shows the fission fragment yield for the thermal fission, neutron-induced fission of uranium-235 in a reactor. It is apparent that the distribution of fragments is not symmetric. Two abundance peaks exist, one around 90 and the other one around a mass number of 140. On the right, several typical fission reactions are illustrated. They are just a few examples of many others. In all cases, the reactor fuel uranium-235 absorbs a neutron and is converted to uranium-236 in an excited state. This excitation energy is sufficient to drive the system in a statistical fashion to scission into two fragments and additional neutrons. These additional neutrons sustain the chain of fission reactions. For example, the excited uranium nucleus may scission into iodine-131 and yttrium-102, plus 3 additional fission neutrons. As its location on the fission yield plot shows, iodine-131 is not the most abundant fission fragment. It is, however, very important because of its short half-life and therefore its large radioactivity. Because of its presence in reactor fuel and due to its relatively high activity, iodine-131 is also an important nuclide in the fallout from reactor accidents and nuclear weapons explosions. This map shows the fallout of iodine-131 following the Fukushima emergency. The wind conditions were such that, as with other fallout products, iodine-131 was mainly driven out to sea. This was fortunate since it reduced the exposure of the population. As in medical radioiodine treatment, the fallout iodine-131 accumulates in the thyroid and decays over 2 to 3 weeks, thus causing damage to healthy tissue. This is the reason why typically iodine tablets are given to a population after a reactor accident to saturate the need of human thyroids for iodine. The radioactive iodine is then not accumulated in the thyroid and discharged quickly by the human body. The second production technique for radioiodine involves inserting a tellurium oxide target in the neutron flux of a reactor. Although natural tellurium contains about 30% of tellurium-130, it is often enriched to have a more effective process. This production target is then irradiated with neutrons. A neutron is absorbed in an N-gamma reaction so that tellurium-130 is converted to tellurium-131. After de-exciting via gamma emission into its ground state, this nuclide decays via beta-minus decay to iodine-131 with a half-life of 25 minutes. The iodine is extracted as gas and converted to sodium iodide or attached to a pharmaceutical to form meta-iodobenzylguanidine, MIBG. The beta electrons from the decay of iodine-131 have relatively high energy and attack the cells of the cancer tumor. After administration, the patient becomes a radioactive source and must be kept in isolation. Iodine-131 is not only used in treatment, but also in medical diagnosis. After attaching it to certain radiopharmaceuticals, it seeks out tumors in the human body, and those tumors can then be visualized using scintigraphy with a gamma camera. Two such scintigraphs are shown. Apart from the expected uptake by thyroid and bladder, the radioisotope accumulates in the tumor, which can thus be identified. The decay scheme shows the decay types and energy levels associated with the decay of iodine-131, which decays with a half-life of 8.0228 days. In particular, one of 3 beta electrons is emitted. Most of the time, at 89.6%, iodine-131 emits a 606 keV beta electron into an excited state of xenon-131, which then decays via gamma emission, typically with a 364 keV gamma photon. The two alternative beta decays at 0.39% with 807 keV or at 7.23% with 334 keV also are followed by gamma emissions. Particularly interesting from a nuclear physics point of view is the beta decay at 807 keV because it populates an isomer of xenon-131, xenon-131M, which has a half-life of 11.9 days. With a significant delay, it then decays into the xenon-131 ground state via a 164 keV gamma emission. The emission of a gamma photon is, however, not the only form of de-excitation in this case. In fact, most of the time, the de-excitation involves internal conversion. This is apparent from the very small fraction of 0.021% associated with the gamma ray. The long half-life of the isomer xenon-131 has to do with the fact that transitioning from there to the ground state involves a considerable restructuring of the nucleus. It is clear that iodine-131 is not only a very important medical isotope, but also a good example of many nuclear physics concepts. The medical isotope iodine-131 can therefore serve as an example for several important nuclear physics concepts, such as the radioactive decay law and activity, however also for activity in a decay series, which is described by the Bateman equation. In the second production technique via tellurium, initially tellurium is produced, which then decays into iodine, which then again decays into xenon. Iodine-131 does not have a single decay path, but a number of them, and the relative importance of those is determined by nuclear structure, which tells us what type of decays occur. Nuclear reactions are important in this context because they are required to make this nuclide. Both production techniques, either via fission fragments or via tellurium and gamma, requires a high neutron flux. This is only possible in a nuclear reactor. The decay of iodine-131 not only involves beta decays, but also gamma decays and internal conversion, which produce Auger electrons and X-rays. The effects of all those radiations on tissue are important when administering iodine-131. In order to do this responsibly, one therefore has to understand the range, the absorbed dose, and the equivalent dose associated with all those types of radiations.